Good morning. My name is Dr. Wilma Augustyn, and I will be presenting sample preparation and chromatographic analysis. I'm focusing on plant extractions and separation and identification of compounds, but this is applicable to any separation that we have that you're going to perform. As I said, I'm presenting the sample preparation and chromatographic analysis. Now, whenever we do a metabolomic analysis, we have a few general steps that you're going to follow. The first would be the preparation of the sample, and then analysis of your sample, which would be giving you data, in our case, chromatographic data, and that data we are then going to process in an effort to get, well, to mine the data to get the information that we would like, either metabolites that we're interested in or identification of metabolites. So the first section that we start with will be sample preparation. Now, sample preparation is the absolute beginning of your project or your experiment. So if you want to do that, you have to keep in mind these two quotes. The first one from Basil Walsh, which says, if you don't know where you are going, how can you expect to get there? And then from Tariq Sadiq, if you are failing to plan, you are planning to fail. And this is very important with your sampling, because if your sampling step is incorrect or your sample handling is incorrect, you cannot get data that you can use you will not be able to get the data that you require. So when we're looking at sample preparation, there are 4 steps that we normally go through. The first one is your harvesting. It's that by, and because we're looking at plant samples, the first step would be harvesting, but the first step would be then acquiring your samples, which could then also be human blood, it could be blood, it could be animals, but it could be, the first step is acquiring your sample. Then after the second step would be drying and extraction, and we could stop at extraction, or we could have a cleanup procedure after the extraction. But what is very important, that whatever you decide on the steps of your sample preparation, they must be similar throughout the project. So all steps of a metabolomic study must be standardized, so that allows you to compare your data generated at different times and places. So if you want to collect samples, plant samples in different seasons, and you want to have winter samples and compare that to summer samples, what you have to have is you have to follow the exact same procedure so that you can then compare the data that you obtain. So your first step would be harvesting. Now, once again, in plant setup, what is important is the time at which you would sample your plants. You all know that, and you should know that there's a difference in the metabolites produced by a plant early morning to in the afternoon to just before sunset. So if you don't set a time at which you will be collecting your samples, you cannot compare the results that you obtain, because in the morning you would have different metabolites to what you would have late just before sunset. So it's important that if you're going to decide on what time you are collecting your samples, that throughout the project you will use that time to collect your samples. Then the next step is, which plant part are you going to use? You can either use the flowers or the leaves or the fruit or the roots. But if you decide on a plant part, you have to use that plant part throughout. What is even more important, if you decide on a plant part, say for example you decide you're going to use leaves, then you could have either young leaves or old leaves, and that will make a big difference on the results that you get. on the right-hand side, you have 2 overlaying chromatograms of mango leaves that would sampled, flush mango leaves, very small, young, very young leaves, just opening up. And then we have mature leaves. And while we look at the 2 chromatograms, you can see that mostly we have the same compounds, but we have much higher levels in flush leaves than we have in mature leaves. So keep that in mind. The moment that you have decided on a plant part, you have to then specify the developmental stage of that plant part and use that throughout the study. Then if you have decided you're now using your leaves or your roots, as soon as you have sampled that, you should freeze it, because that will stop all enzyme activity, and therefore you won't be producing metabolites after sampling. The next step would be drying, and in the drying step we are removing water so that we can stop enzyme reaction. You remember I said if we get the plant, we immediately freeze it, but the next step would be a freeze drying step, where you would where you would remove water. So you want to remove the water so that you can stop enzyme reactions, because your enzyme reaction would take place in an aqueous medium. So if you, and apart from that, if you have lots of water in your material that you collected, that can play a role with the quantification of your compounds in the end. Because if it has more water, then it would be more dilute. Whatever if you say you're going to weigh 10 grams, a dried sample of 10 grams would be way more concentrated than a wet sample of 10 grams. And then water will also affect your NMR and your MS analysis. So we prefer not, we have to remove the water. Now, water can be removed by freeze drying, which is the one that's most often used, because you have your samples frozen already, and then you remove your water while it's still frozen. So you ensure that you don't have a step where you go back through a heated sample back to room temperature. If you have sampled say fruit, for example, and you want to determine what happens to the peel of the fruit where it is not freeze dried, you can then also use either solar drying, oven drying, microwave drying, or air drying. On the right, we have a picture of a solar dryer, which uses the energy of the sun, and it dries your material very fast. And then we get to the extraction procedure. Now, I just want to go back a little bit, but after the drying of the plant parts, it should be you should grind it until it's a very fine powder, and then afterwards you should put it through a sieve, say a 250 micron sieve, so that you sieve it and you only have all your particles will have the same size. That ensures that you have your extract would be the same constantly, because if you have bigger particle size, you might just have less metabolites extracted than with a finely ground powder. So after your drying step, you have to ground your samples, and then that sample must go through a sieve to ensure that you have the same sample or particle size. Then when we get to the extraction step, what we have is, you all know from chemistry 1 that like dissolves like, if we look at the polarity of the compound. Now, when we extract, we would like to extract as many metabolites as possible. And unfortunately, with one solvent system, you would not be able to do that, because you would either extract polar compounds or non-polar compounds. So keep in mind that when you have an extraction, you either have to use more than one solvent, more than one extraction procedure, or you have to focus on a specific type of metabolite for your extraction. And then, apart from when you have now chosen the solvent that you want to use, you have different procedures in which you can do your extraction. You can have a microwave extraction. You can just heat your sample for a while in the solvent. An example of that would be distillation. Then you can have ultrasonication. You can also just have a longer extraction time where you might extract where you shake your sample for overnight or so. However, if you choose either distillation, which is a big problem with artifact formation, or very long extraction times, it is possible that you find that you get artifacts. And artifacts would be the formation of compounds that you would normally not see in your metabolic profile. Or a compound that's normally not found as a natural product, because it might be something that broke down that in the process of this either long extraction time or the heating process. So when we look at GCMS, we are looking basically at volatile compounds. That would be compounds with boiling point of about maximum 250 degrees Celsius. Now you are able to analyze for more polar compounds using GCMS, but then you have to derivatize the compound. So for example, say you have a carboxylic acid and you want to analyze by GCMS, the longer chain carboxylic acids would have very high boiling points and will not be volatilized in your GCMS in the GC procedure. So what we can do is we can react the carboxylic acid with an alcohol to form an ester, which is a non-polar compound with a lower boiling point, and would be able to analyze on GC. Then if we have more polar compounds, but we can use LC, but a liquid chromatography has a very wide range of compound or columns that can be used, and therefore very wide range of metabolites that can be analyzed on on LC. What is important that we have to remember that the solvent that we use for your liquid chromatography must be miscible in the mobile phase that you're going to use in the end. If we want to do analysis using NMR, then there would be less limitations except for very high water content. Now, if you look at a liquid chromatography extract, you are going to need more, well, you're looking at more polar compounds. And a method, there are various methods that you can use for your extraction. You would see that you would have a more polar solvent mixture. For example, the one that I often use is the one where we have acetone, methanol, and water in a ratio of 7:1, which is quite polar. And this is specific for phenolic compounds. And as soon as you have decided on your solvent, then you can decide on the different extraction procedures. You do not have to use this mixture. You could use, and very often, methanol in water is used or ethanol in water. But you can see that what we basically have is a polar solvent system. Then you can use that solvent to either go to a microwave extraction or liquid-liquid extraction. Now, if we use a liquid, either the microwave extraction or just a liquid-liquid, you would have your liquid and you have your extraction procedure where you either use ultrasonification or your microwave extraction. And then afterwards, after you get your extract and you have filtered it from your solvent, from your solutes, or the section that did not go into the would not be extracted, that would be your plant parts. You can also do a liquid extraction on that solvent if you want to remove something specific. So say, for example, you had an extract and it contains a lot of chlorophyll and you want to remove your chlorophyll. Then you can have a liquid extraction where you would extract with chloroform. And your chlorophyll would go into the chlorophyll form layer, and you have removed that very green color from your extract. You could also extract with hexane, and by that you will be removing lipids from your extract. So you can have a clean up procedure by doing a liquid-liquid extraction. You could also take the crude extract that you have from your extraction, any of the extractions that we have discussed above, and put that, which is called the crude extract, and then separate further using a packed column or a solid phase extraction. Well, for solid phase, it's basically a little column in a cartridge, and you would load your crude extract on it the same way that you would do with a packed column. Your metabolites of interest will be absorbed. So if it's a C18 column or it has amino or nitrile groups, which makes it more polar, that will be attracted to the adsorbent inside the column. And then you can wash off your specific compounds one after the other, or group of compounds. So you can decide, I'm going to look at alkaloids which are polar, and I'm going to use methanol for to elute from the column. So there you will be separating in groups of metabolites with more or less the same polarity. After that step, you can then filter your sample and inject it onto the LC. Okay, as I said, with the packed and the solid phase extraction, you will elute with different solvents, and each fraction that you would collect then will contain specific metabolites with specific properties. There are two other ways in which you can clean up your extract a little bit. You can use preparative HPLC, where you also would place your crude extract on the prep HPLC, which means it contains, you can place higher solvent volume, sample volumes on your column, and therefore separate bigger or obtain higher volume and higher quantities of your specific metabolites. And you can also use high performance countercurrent chromatography to once again separate into the different classes, or to remove your chlorophyll in the process or your lipids using either one of those two instruments. If we have extraction for GC, if we have headspace, that's just the volatiles above a liquid. Or if you have solvent extraction, where you now use a non-polar solvent, say you use hexane, for example, these two extracts can directly be injected onto the GC. Okay, it's placed directly. The solvent may be also filtered before you put it onto the GC, but you don't have to have any other cleanup procedures. Then if you have volatile samples such as essential oils, if you had an say distillation to obtain your essential oil, you don't have to derivatize those samples. You can also inject them directly. So it's only when you start getting very polar samples that you have to do your derivatization. So if you have polar solvent samples or polar components with very high molar masses, and that's normally when you start getting your longer chain hydrocarbons, either just longer chain hydrocarbons, or when you have acids of longer chain hydrocarbons, then number one, it would not be volatilized and you would not be separating it, and it could also accumulate into the column, which means it lowers the efficiency of the column. So we don't want to place compounds that will not volatilize onto our GC column. So the first step would be then derivatization with oximes. And then after that, you would follow that with a trimethyl silylation, which replaces your hydrogens on your polar functional groups with a trimethyl silyl group. So then it's non-polar. And this would then allow you to detect polar groups such as amino acids, fatty acids, sugars, and alcohols. However, many plant phenolics will not give stable volatile derivatives. So if we have polar compounds, and especially your phenolic compounds, we prefer using liquid chromatography for our separation. So that brings us to how a GC and an HPLC chromatographic separation will take place, and how can we make sure that we have the most efficient separation of our compounds. Because when you start with your metabolites or you start with your sample, you want to be able to separate as many compounds before it goes to the MS. Even though we know that the MS would be able to distinguish between different compounds in say if you have a peak, but we have a peak overlapping. With MS, you can, the MS are able to detect or to determine different compounds according to the retention time and the mass to charge value of that compound. But you cannot have 10 compounds eluting as one peak. So what we really want is to get a separation, a good separation where we have baseline separation of our components as far as possible. And now this is just a little bit of theory behind choosing our flow rates and choosing our columns to obtain the best separation that we can. In the right-hand corner at the bottom, we have the von Diemter equation. Now, the von Diemter equation would give you an indication, or you use the von Diemter equation to draw the von Diemter plot. And the von Diemter plot we have on the left-hand side. And what the von Diemter plot actually shows you is which is the best flow rate to use for your separation. And this would be for GC as well as for HPLC. So what we do in setting up the von Diemter plot, we would inject a non-retained compound, and we inject our a standard sample, and we analyze. Not a sample, but a standard, so that you would have only two peaks, the non-retained peak and your standard, and you determine, you put in a specific flow rate, and you determine the H value, the plate height, and you plot that, and then you go to a different flow rate. And you would see as you increase the flow rate, you have a drop in your plate height, and we want the lowest plate height possible. And then if we keep on increasing the flow rate, you would see now the curve rises again. So the optimum flow rate would be the one where we have the lowest H value. So when you decide on a separation and you're not sure what you do, what the flow rate should be, or you don't get a separation that satisfies you, start looking at number one, the flow rate, and start with a low flow rate and increase the flow rate up until the point where you get your lowest plate height value, because that shows you, it's an indication of the efficiency of the separation. Now, if you look at your von Diemter equation, you have your three terms, your A, B, and the two C terms, where your A term, you can see what is important in the A term is the particle size. That's the dP value. In the B term, your flow rate plays a big role. And in the two C terms, that's your mass distribution terms. You can see you have your distribution coefficient there. And then you also have, once again, your particle size and your liquid layer onto your stationary phase. That's your dF squared and your dP squared values, and also flow rate. So if you look at the von Diemter equation, what is going to play a role with separation is very important: flow rate, and then also particle size. The smaller your particle size, the more efficient your separation will be. This is just to show you the influence of the different terms on the von Diemter plot. Now remember, the A term we don't get in the plot because the A term has no flow rate as part of the equation. So you can see, if we look at the drop in plate height value, is basically because of the second term, which is your longitudinal diffusion term. And the increase in the plot is once again because of those two mass transfer terms. And so what is important is play around with flow rate to get the most efficient separation. And then other parameters that we can have a look at to determine column efficiency is the first one we have now looked at, which is plate height. And you can see what plays a role in plate height would be the length of the column, the width of your peak, and the retention time. Then we want the plate height to be as low as possible. And then another term is the theoretical number of plates. And the theoretical number of plates, it once again contains the retention time and peak width. And then another way of expressing a theoretical plate would be at half peak width. And the last term, where theoretical number of plates is the length of the column divided by your plate height. And so you can see, to increase N, to increase the theoretical number of plates, we need to have a longer column and a smaller H value, smaller plate height. So with all of this, lots of the equations, but what is important is we want to have the peak width as small as possible, as well as the retention time. Because if the retention time is shorter, your peak width would become shorter. So this is how you decide if you have an efficient separation. If you have very broad peaks, then your W value, your peak width becomes too big, and your H value, your plate height, becomes too big. So you have to change conditions so you can have nice sharp peaks. That's the whole point of an efficient column separation, is to get to a point where you have sharp peaks, well separated, baseline separated, sharp peaks. Now, which variables will affect your column performance? Well, we have discussed theoretical number of plates, which we want to have as high as possible, and then your plate height to be as small as possible. And as soon as you have big plate heights, it is because of band broadening. That's that peak width. Now, what factors will then be influenced by having low H values and no, the other way around, high H values and low N values? Well, your distribution constant will play a role in N and H values. Your alpha value, which is your selectivity factor, which has to do with the properties of your solutes, which has to do with the analytes you're looking at. So it is important to use the correct column for your compounds that you want to separate. And then we also have the retention factor, which has to do with how long it takes for your sample to, for your specific compound to elute. And this has to do with, obviously, the solute and the column, because it's the attraction between the compound and the column that you have chosen. Now, both the retention and the selectivity factor can be manipulated by changing your temperature or the composition of the mobile phase. So this is the next step. So you first check your flow rate, and then you would start playing around with a mobile phase or your temperature program in GC. If you have done that extensively and changed the programs for both LC or GC, either temperature or the mobile phase composition, and you don't get a separation, a good enough separation, you must realize that now you have to start looking at a different column. So if we want to change our number of theoretical plates, if I said we change the column, we can also choose a longer length, because immediately if you have a longer length, then you would also have a better separation. Just keep in mind, if your column length becomes longer, you are increasing the time of your separation. And if you have lots and lots of samples, you can't have a run taking 60 minutes for the separation. Then we said we can also change the plate heights by playing around with the flow rate. If we want to change the column, we have to look at particle size as well, because as soon as you choose a smaller particle size, then your separation will also be better. And then for LC, we can change the viscosity of the mobile phase, which would then have an influence on your DM and DS values. And you can also change the thickness of the film absorbed onto your stationary phase, but this also goes with the packing material. So this is the methods that you can start looking at if you don't get an efficient separation. We looked at variations in your plate height, and remember, if we look at that van Deemte equation, if we can change H, the plate height, by looking at our flow rate, but also looking at the particle size. And then for LC, we can reduce the solvent viscosity, and that increase the diffusion coefficient in the mobile phase. And then we can look at, with GC, changing the temperature conditions. So we normally use a gradient, and we play around with that gradient to get the best separation. And then if we look at HPLC, we can change our solvent composition. Okay, so now we have decided on a method. I just want to go through a little bit of troubleshooting on GC and LC. Is what do you have to look out for? What do you have to do to your instrument to ensure that you have the best separating conditions? So number one, for GC, I'm going to look at the different maintenance that we have to maintenance that must take place. Then what column do you choose, and the temperature program, as well as the MS conditions. Okay, so when we have a GC, and this is something that you have to check for routinely, you have to check for gas leaks, and you can check for gas leaks by just everywhere where you have a connection from the cylinder up to the instrument. Just spray a little bit of a soapy water on the connection, and if bubbles form, then you know that you have a gas leak there. Then you must check that the flow rates that you are recording corresponds to what is on the instrument, either the flow rate or the pressure that you put in. Then in most cases, you would have gas filters between your cylinder and your instrument to make sure that it absorbs water and oxygen and carbon compounds that might be in the gases. I know that we buy very high quality gases for GC, and we expect them to be clean, but they're never clean. So we put in the filters to make sure that we have that it absorbs all these components that's in the gas. As soon as the gas filter has changed color, the indicator in the filter changes color, then we know that we have to replace those filters. Then we have to replace the septum as soon as you see that you have changes in the peak shape, where you either have ghost peaks forming or you get tailing, mostly tailing of your peaks. Then it's a good indication that you have to replace your septum. And there at the top photo, you see how easy it is to replace the septum. And then you also have to clean the liner every now and again. Once again, when you see changes in the shape of your peak, then it's a good indication that the liner is not clean, and you can just remove the liner, clean it, salinize again to make sure that you don't have polar active sites on your liner. And then especially if you see that your column performance is not what it's supposed to be, you can bake out the oven overnight. So you can put the column at a higher temperature overnight so that any compounds that has been absorbed onto the column and has not been volatilized can then be volatilized and be baked out of the oven. And then another good routine procedure is to determine your number of theoretical plates every now and again using the exact same conditions. So you would use the exact same standard that you used 6 months ago to see if the column is still as efficient. So if you determine your theoretical number of plates, it's in the same order than it was previously, then you know that the separation is still efficient. You still get the same separation that you did previously. Then you have to clean the syringe, the waste solvent vials, the washing solvent vials with ethyl acetate on a weekly basis, because no point that those vials are dirty and that's what you use to clean your syringe. Then your vacuum pump air filters must be checked at least twice a year. And then the vacuum oil, you have to check the vacuum oil for the color and the viscosity on a monthly basis if you use the instrument quite often. The column is the heart of the separation. If you have the wrong column or the wrong temperature program, then you won't separate your compounds and the data you obtained would be meaningless. So what is important is that you have to choose the right column and then the correct temperature program for that column and then your MS conditions for the detector. So when we look at GC, we have two types of columns. We have packed columns and capillary columns. Now, packed columns and capillary columns, you can either get them as gas liquid or gas solid columns, but packed columns would be a glass column and it would be about 5 meters long and it has particles packed inside the column. And this is not often used anymore, but it's used in many cases for environmental gases, which then can absorb on that packing material. For most of the other analysis, we use capillary columns. And once again, for a capillary column, you can have either gas liquid or gas solid columns. When we have a packed column, it could be gas liquid or gas solid, and for gas liquid you can have wall-coated open tubular columns or support-coated open tubular, and for gas solid you can have a porous layer open tubular columns. We normally use the capillary columns and we normally use either wall-coated or support-coated open tubular columns. And then to make sure what type of column you have, all columns, GC and HPLC, would have a little label on it, and you can go and look at the label and it would tell you which type of column you have. In this case, it's a methyl silicon gum column, and the length of the column, it's a 5-meter column with a 0.53 millimeter diameter and a particle size, or the film thickness in this case, of 2.65 micron. So you get all the information. So when I say after you have tried using a different program to separate your compounds and you still don't get an efficient separation, you can look at what was the column that I used. If I need a longer length, if I don't need 5 meters but 10 or 30 meters, then you know you can take that column and just go and buy a column that has a longer length, or change your stationary phase completely. Now, when choosing the column, your analytes must be compatible with the stationary phase. So if your stationary phase is polar, you're going to have polar molecules that's going to be separated on it. Once again, like dissolve like. You have to have your analytes must be attracted to the stationary phase, because if it's not, it's just going to run through the whole column with the mobile phase. So when choosing your stationary phase, you choose something that would correspond to the analyte's polarity. So if we choose polar stationary phases, we have functional groups as cyano or amino, carbonyl or hydroxyls. And your analytes that you will separate would be alcohols, acids, and amides. Then you can have a medium polarity stationary phases, which contains ethers, ketones, and aldehydes, or non-polar stationary phases that will contain hydrocarbons and dialkyl siloxanes. And for that, you will separate non-polar analytes, such as hydrocarbons. Now, when we have GC, if your match between your analyte and your stationary phase is good enough, then your order of elution would be according to boiling point. And you can go and check that. If you have, say, terpenes that you want to separate, you would see that the lowest boiling point terpene would be the first one to elute, and the highest boiling point would normally be the last one, because you have attraction of your terpenes to your stationary phase. And then as you increase the temperature, it becomes volatilized and it starts moving in the mobile phase. So the order of elution is according to boiling point. Now, in a general lab, you would have a few normal columns or columns that you would generally find. A favorite one is the DB1, which is a polydimethyl siloxane, and it's a completely non-polar, and you're going to use it as a general purpose non-polar phase. So that would be very efficient for alkanes and hydrocarbons in general. Huh? Then you get a DB5, which is another column that we very often use. And for that, 5% of your methyl groups were replaced with phenyl groups, and you now have a polyphenyl methyl dimethyl siloxane column. And for this, you can now start analyzing for more polar compounds as your fatty acid, methyl esters, terpenes, and alkaloids. And then you can get a 50% phenyl replacement, and that would be then for more polar compounds such as pesticides and steroids. You can use a trifluoropropyl. That would be for your chlorinated aromatics and your nitroaromatics and your alkyne benzenes. Another favorite, so normally in a lab you would have a DB1, a DB5, and a carbowax column. The carbowax would be a polyethylene glycol, and you would be able to separate acids, alcohols, ethers, and essential oils on it. And then you can also have a cyanoallyl group for free acids and alcohols. So now we have chosen our column, and we have to determine the conditions to separate our compounds. Now we are well, number one, if your injector port must be 50 degrees higher than the boiling point of your least volatile compound. So it must be 50 degrees higher than the highest boiling point compound. Now, I know that when you do a separation or extraction, you're not sure about the temperature of your highest boiling point compound. So if you use 250 or even 300 degrees Celsius, not more than that, maybe 250 degrees Celsius for your injector, you ensure that all your compounds of interest will be volatilized and then placed onto the column by your flow of gas through the injector onto the column. The compounds that has not been volatilized will stay in the injector port and can be flushed out of the port. So we ensure that you have all the compounds entering the GC and is placed onto the column. Then we have to choose the column temperature. Well, we normally start with a temperature lower than the lowest boiling point, which means we are condensing all of our sample onto the column. So it goes from a gaseous phase to a liquid phase. That ensures that we focus that sample and we have a nice tight zone that enters the column and moves into the column. So we start with a cool temperature lower than the lowest boiling point compound, and then we increase it up to a temperature higher than the highest boiling point compound to make sure that we are separating, or we are removing all the compounds that we placed onto the column from the column. And the detector must be 20 degrees above the injector temperature. So if our injector temperature was 250, your detector temperature must be 280 degrees. For your mass spectrometer, your transfer line temperature at about 280 degrees Celsius, your ion source temperature at 250 degrees Celsius, and then you would adjust for your solvent delay. We don't want to see the solvent because the solvent would flood the ion source. So what we do is you adjust, you have a solvent delay. So we only start detecting after the solvent has separated through the column or has been eluted through from the column. And then you normally have a mass spectral acquisition between 85 and 500 Dalton, and your electron ionization energy at 70 volts. The ionization for GC is a very hard ionization, and it fragments your compound completely. So we're only looking at up to 500 Daltons because that's our compounds mostly that we're interested in, compounds that would be volatile. And for the compounds that were not volatile that we derivatize, because of that hard ionization, we are breaking off that trimethylsilyl part, and we then only have the compound. So we're looking at between 85 and 500. Lower than 85, you might get fragments of your trimethylsilyl group. So normally we work between 85 and 500, but keep in mind you have to look at where your compounds of interest would, or the mass of the compounds of interest would be. Then after you get your compounds, after it went through the detector and you can see them, you can identify the compounds using either libraries such as the NIST library or Mass Finder, or you can inject authentic standards. And if you get with the authentic standard, same retention time, same fragmentation pattern, then it's the same compound. And then you can also use an automated mass spectral deconvolution system, identification system, the MDIS system, to identify your compounds. What's important when we look at the mass spectrometer is that the information that we get is, that we look at is on your mass to charge ratio. So it gives you the mass, it gives you the retention time, and then it also gives you a signal amplitude. So it gives you an indication of the concentration. So a mass spectrum initially would look the same as a chromatogram. You would have your base peaks, and then you can look at each peak and you can get the fragmentation pattern of that peak. But if you look at your spectrum, initially you would get your mass, you would get the retention time, and you would get the idea of the concentration of your compound. So these coordinates then would be aligned when you do the data processing to get these so that you can go to multivariate data analysis. You take these coordinates and the mass peaks are correlated, and we look for a specific trait that we filter out and then identify by your accurate mass. And your MS, after that, you can use an MS fragmentation pattern to confirm your standards. So, but for that multivariate analysis, what we need is the mass to charge ratio and the retention time. And obviously the quantity, because according to that, you will then be able to identify the compound and quantify the compound. Okay, the next section that we're going to look at is liquid chromatography. Now, with liquid chromatography, we have a wide range of compounds that can be separated. It would be from non-polar compounds all the way through to polar compounds and even ionic compounds. And all of this can be separated by choosing the correct stationary phase. So for non-polar compounds, for where we have adsorption, we have where you have a solid stationary phase and not a liquid layer. Then we can have partition chromatography, which is the one that we most often use, where it can either be reverse phase or normal phase separation. And then completely to polar ionic compounds, we can have ion exchange. And then what makes HPLC so much nicer than GC is we can separate very high molar mass compounds, either by gel permeation for water insoluble or non-polar compounds, or gel filtration for water soluble compounds. So a wide range of, by choosing the correct column, we can separate for a wide range of compounds in our sample. So we're going to go through the same procedure for GC. First step is what's the different maintenance, or what do we have to look out for liquid chromatography, the choice of the column, method development, and MS conditions. So the first step, whenever you prepare your mobile phase, you have to make sure that, well, because when you mix, normally you would prepare a water phase and a more non-polar phase, say for example acetonitrile, and then when you have your gradient, you mix these two solvent, and in the process of mixing, you might get that you have heat generated, and that would cause the gas that was dissolved in the mobile phase to become dissolved, and it forms bubbles. And these bubbles will then travel through your column. This will cause inconsistent flow rate and false peaks on the chromatogram. So it's very important that you would remove the bubbles that will interfere with the performance of your detector, as well as have an influence on the flow rate. So you can remove the bubbles by either sparging, that is by bubbling an inert insoluble gas through the mobile phase. So you would bubble nitrogen or argon or helium through your mobile phase. Or you would just place, after preparation of your mobile phase, you would place it into an ultrasonic bath for a while and you would see the bubbles forming. Or many instruments would have a built-in degasser that would be in your vacuum pumping system that will then degas your mobile phase. Then you also have to filter your mobile phase, and you filter it through a 0.45 micron filter under vacuum. This would not only dissolve air or your other gases that you would have because of that vacuum suction, but it also removes dust and other particulate matter that you have that can block your column and your tubes. It also removes microbial organisms that you might have. I know that many of you would prepare a mobile phase, your aqueous phase, and many days later you would still use that same layer, that same water phase, and it might be that you have growth taking place, microbial growth. So if you want to use that same aqueous layer, you can just filter it through a 0.45 or even a 0.2 micron filter to make sure that you have no particulate matter inside your mobile phase. Then for the pumping system, well, for your pumps, it's also a good idea to filter your solvents, because once again, you don't have then water that contains bacterial growth in your solvents. You would also not leave water in the pump after you've done an analysis. Say you have done an analysis on Friday afternoon and you would leave it in water until Monday, because once again, you can have bacterial growth starting to take place in your pump. You will never leave buffer in the pump. If you want to not change the buffer, say just rinse it out with methanol or acetonitrile, you could put the buffer on a very slow flow rate of 0.1 milliliter per minute or so and keep it running and not standing, because what you can have is precipitation of your salts that's in the buffer in the pump. It's always a good idea that if you have used a buffer is to rinse it with water after the analysis, and then you never leave solvents containing corrosive acids in the pump, because obviously you would have corrosion of your pump. Then if we look at the columns, to choose a column, now normally the partition chromatography that we mostly use would either use normal or reversed phase packaging. Now normal phase, initially when chromatography started out, we had a very polar packing material such as silica gel and alumina, and therefore your stationary phase was polar, and your mobile phase therefore had an opposite polarity, because now your compounds would be attracted to the polar stationary phase and it will elute with a mobile phase, which is non-polar. And then you can start increasing the polarity of your mobile phase so that you can elute your more polar compounds. So your stationary phase would be polar and your mobile phase would be something like hexane and ethyl acetate, and then going to dichloromethane, methane and chloroform, which would be more polar. We also have reverse phase chromatography, which is the one that we most often use because it's more versatile than the normal phase, and your separation is better on a reverse phase. Normal phase would be very strong attraction and absorption, and you can have distorted peaks, while reverse phase, because of the wide variety of mobile stationary phases, we can get better separation. So the stationary phase that we have for reverse phase chromatography would be non-polar, and your mobile phase would be polar, either water, methanol, acetonitrile, and buffers, once again going from very polar, which is your water, to a more non-polar, which is your acetonitrile. In normal phase packaging, we have a stationary phase that contains functional groups such as aminos, diols, and nitriles, and that would go then from most polar to least polar. We often get peak tailing in normal phase, and that is because we have a strong interaction taking place. Remember, we have now polar groups and we have hydrogen bonding, and so there's a strong attraction between your stationary phase and your compounds, and therefore the compounds is very reluctant to go from the stationary phase into the mobile phase, and what we find is peak tailing taking place. Your elution would then be your non-polar solvents, such as the hexane, chloroform, and diethyl ether. And for reverse phase packaging, we have a wide variety where we can have C18 columns, octadecal. We can have C4, C30, octyl, butyls, trimethyls, phenols, all of them polarity a little bit different. The longer the chain, like a C18, would give you better separation than a C4. But obviously, whenever you get better separation, you have to keep time in mind, and you can have a longer time for separation. In reverse phase, we don't have strong attractions. We don't have that hydrogen bonding. What we have is mostly van der Waals forces. And so the peaks would be more symmetrical than in a normal phase separation. And the major advantage of reverse phase is that you have water as a mobile phase. And number one, so it's inexpensive. Water is not expensive to prepare. And then it's non-toxic. With normal phase chromatography, you have to have special procedures to dispose of your hexane and your chloroform, while with water as a mobile phase, it is non-toxic, and what is important is UV transparent. If we use something like acetone and hexane, it is not UV transparent, and therefore you can't use it for your you can't use a UV detector. So it is in water. The reverse phase is the preferred separation at this stage. Now, method development in LC is way more complex than with GC because of the interaction of your component with the mobile and the stationary phase. Remember, in GC, the interaction is basically your analyte with your stationary phase. And as soon as the temperature is high enough, then it moves into the gas, which is your mobile phase, and the mobile phase just carries the sample out. So with GC, your temperature program must just be long enough or specific enough so that you can get all your samples being separated, or all your analytes being separated. But with LC, we have a different, we have interaction between the mobile phase, the analyte, and the stationary phase. So the analyte sort of would be attracted to the stationary phase, but it's also being attracted to the mobile phase. And those conditions has to be optimized so that you can get your best separation. Once again, your stationary phase should roughly match the analyte. And your mobile phase must have a different polarity. So once again, we want attraction between our compounds and the stationary phase. And then we change the mobile phase conditions so that we can get the analyte moving from the stationary phase into the mobile phase. Now, if we say we're not going to, the stationary phase would be different from the analyte, you can think, now we don't have attraction between the stationary phase and the analyte, and we will have no separation because your analyte will just run with the mobile phase because it would prefer the mobile phase, which is non-polar, to the stationary phase, which is polar. And you would have very short retention time. All your compounds would just elute at close to the non-retained compound. If your stationary phase is too much like the analyte, then we have strong attraction between the stationary phase and your analyte, and it takes very long for your separation to take place. And therefore, we have to change the mobile phase composition, and therefore you would make the mobile phase more non-polar so that we can remove the samples from the stationary phase to the mobile phase. So for method development in LC, you have to blend the polarities of the mobile phase and the stationary phase and the analyte. And with that, you would have to have trial and error experiment. So you would maybe start with a program of an hour to just see how many compounds you have, how long it takes for your compound to elute. And then you would start playing around by increasing your acetonitrile, maybe making it much higher so that you can get rid of the compound or get the compounds eluted that is strongly attracted to the non-polar stationary phase. So we always start with a high concentration of your water, which would then elute all the compounds that's not attracted to your stationary phase. And after that, we increase the non-polar component of our mobile phase so that we can elute the compounds attracted strongly to our non-polar stationary phase. So once again, we have to look at the conditions for good resolution. And once again, we're looking at the number of theoretical plates, the retention factor, and the selectivity factor. Now, the retention factor and the selectivity factor can be manipulated by mobile phase composition. So as soon as we've chosen a column, we can play around with the composition of the mobile phase to ensure that we have the best separation. And then after you've done that extensively and you have worked with your mobile phases, and if I say change the mobile phase composition, you don't only have to use water and acetonitrile, you can have tetrahydrofurane in the mixture or methanol. Play around with 3 mobile phases and not 2 only in the composition. And online you would be able to get a solvent triangle, which would give you an indication of how you can play around with your different composition of your mobile phases to ensure the best separation. And then alternatively, if you've done that, you might think of using another column so that the attraction is either less or more. Now, when we look at mass spectrometry, we can't use that very high electron ionization that we use for GC because of our solvents. So we're using a softer ionization technique, which would be either electrospray ionization or atmospheric pressure chemical ionization. Both of them softer ionization techniques, which would actually not fragment your compound, but just give you the mass, the base peak, the big one. You can either run it in positive mode, which means your compounds would be protonated, or in negative mode, which will show you that you have deprotonated your compounds. Now, the compounds that you can see using LC-MS would or separate and detect would normally be the most economically important group of plant secondary metabolites. So this was why LC-MS would be favored above GC-MS, because we are looking for plant extracts. We are looking, unless we're looking for essential oils, then obviously GC-MS would work. But if we want to see differences in the secondary metabolites, we are looking at LC-MS for our separation, and we can then detect alkaloids, saponins, phenolic acids, etc. Then if we look at the mass spectrometer, to compensate for drifts in your instrument calibration, we use a compound of known mass, and this is called the lock mass. And that gives you an internal mass standard for every spectrum. So you add that little bit, and what we normally use is leucine N-caffeine. And that's your lock mass solution, and that gives you, it locks the mass, and therefore the instrument has that as a standard through every spectrum that it has. If we look at the conditions for the electron spray, you have your capillary voltage somewhere between 2,750 and 3,500 volts. Cone voltage 35 volts, your source temperature between 100 and 120 degrees Celsius, your desolvation temperature between 250 and 350 degrees Celsius, your cone gas flow between 20 and 50 liters per hour, your desolvation gas flow between 500 and 600 liters per hour, and your mass to charge range would now be much bigger than for GC. It would now be between 100 and 1,500 Dalton, and a scan time of 0.5 seconds. This is just to give you an idea of what the conditions would be for your MS. Now, after you have done your separation and you have your compounds, in many cases, we would put it through another MS so that we can get a fragmentation, because in the first step you have a soft ionization, which would just give you basically your mass peak. Then we would put that through another MS separation, where we have a harder ionization, and there you would have your fragmentation pattern, and then you can use your fragmentation pattern to identify the compound. It's much more difficult to use LC-MS for identification than GC-MS. GC-MS, we have a fragmentation pattern, and we have a library to identify the compounds. With LC-MS, you have to have a second step, a second MS, to get a further fragmentation that we can use for identification. Now, when we do that, we can predict the elemental composition of your mass peak of interest from your accurate mass calculation. Then we can get the MS fragmentation, and with that, if you have another detector such as a UV detector, you can have your absorbance spectra as well, and through that you would be able to identify. So you have your mass peak, so you know what your mass would be, you know what your fragmentation pattern would be, and you have your absorbance, and through that you would try and identify the compound. You can also use your elemental formula to search the internet or commercially available compound databases, as the one database of natural product, which you can find on CD-ROM, to look for your specific compound. You can also use to identify specifically plant metabolomics, and this link that I have here is, or site, is specifically for tomato plants, but you could use that one. It's available, it's for free. You can use that to determine, to identify your semi-polar metabolites that you have separated. So there are 2 steps that you can follow to identify the compounds that you have isolated in your extraction and analysis procedure. That's it for me. Thank you for Metabolomics South Africa for the opportunity to discuss GC and LC separation, and then my place of work, Tshwane University of Technology, which gives me the opportunity to do metabolomic research. And then if we have any questions, I will be available this afternoon after Dr. Maxine Sandasi's presentation, so that we can discuss any questions you might have on GC and LC separation.